Yeah.
Yeah, okay, great. So welcome to this talk of the Israel Algorithmic Game Theory Seminar. Today, our own Sigal Oren will speak about mechanism design with moral bidders. So welcome, Sigal.
Thanks, Moshe. Good. So many of our works in algorithmic mechanism design look for truthful mechanisms. So you can say that truthful mechanisms and designing them are a holy grail of algorithmic mechanism design. And even if we just look at this seminar, so about half of the talks so far discuss truthfulness. And one important underlying assumption when we discuss truthfulness is that if we are not going to incentivize our bidders properly, then they are not going to tell the truth. So if they have any reason to lie, any lie that can increase their utility even slightly, then they are going to lie. But is it really the case? Recent literature in behavioral economics suggests otherwise, and let me survey some of this literature. So in a now classic experiment that were first done by Fischenbacher and Forney, they did the following. So participants were asked to roll a die. So this is a regular six-sided die inside a cup. And then they were asked to report the results. So the reason that they were asked to roll the die inside a cup is that this way, they are the only one that see the result. And then the payoff is determined according to the number rolled. So the higher the number, the higher the payoff is. What's nice about this experimental setup is that even though on the individual level, we don't know if a certain participant lied or not, when we look at all the participants that aggregate, since we know the distribution of true values in the six-sided, when you roll a six-sided die, then we know the deviations from what we expect if the participants report truthfully. And this experiment was run many, many times in different countries, different experimental setups, so like different reward distributions. It was done with a die and also with a coin, so there are only 2 states and so on. And about a year ago, Abel et al. Took all of this vast body of research that was done on this experiment and did a meta-analysis of all this information. And together with this meta-analysis, they created a really nice website that enables you to visual data from different experiments. So what you see in this picture is just data ran from extracted from experiments that were ran in Israel. Each color corresponds to a different treatment. And the columns here, you can see correspond to say 1, 2, 3, 4, 5, 6. So the different numbers on the die. And the dashed line here is what the fraction of reports of each number you would expect roughly if people are reporting truthfully. So this line is like 1/6. Now, there are 3 things that are obvious from this graph. First of all, people do lie. You see in all of the experiments that there are some values that are over-reported and some values that are under-reported. And second of all, so for example, if we look at the value of 5, then we can see that there's quite a large gap between what you would expect in truthful reporting, which is the 1/6, and what you actually get in some of the experiments, which is getting close to 40%. Now, what you can also see here is that people do not lie to the full possible extent. So kind of the difference here of over-reporting 5 is much larger than the over-reporting of 6, for example. And when Abel et al. Did this meta-analysis, they find out that in general, participants only collect about 25% of potential gains from lying. So to collect all potential gains, they should always report 6. They don't do it. So they don't lie to the full extent that they can. Here's another experiment related to lying. And this one, the experimental setup is slightly more complicated. So now we have 2 participants. This experiment was run by Uri Gnizi on students in the Technion and Haifa University in 2005. So one of the participants is the sender, and the sender is the one that has all of this information. So there are two options. Each option dictates the payoff of each of the participants. So in option A, the sender gets 5 and the receiver gets 6. And in option B, the sender gets 6 and the receiver gets 5. So this is the sender. The sender has all of the information. And now the sender gets to send a recommendation to the receiver. And she can choose one of the following two messages. So she can either send a message, option B will earn you more money than option A, or the reverse message. So option A will earn you more money than option B. Now, the receiver knows that the sender has all of the information. It knows that the sender knows this table, but the only information he gets is the recommendation. And based on this recommendation or not, the receiver needs to decide one of the options. So say he chose option B. So after he makes this choice, the payoff are realized according to the option that he chose, and each one gets his payoff. Now, in all of the treatments, the option that gives more money to the receiver is option A. So a sender that sends the message, option B will earn you more money than option A, is lying. Okay? He's not telling the truth to the receiver. Now, one important assumption in this experiment is that the senders believe that the receiver is going to follow the recommendation. And indeed, when asked, about 80% of the senders do believe that the recommendation will be followed, and pretty similar when you actually look at the reports, about 80% of the receivers also follow the recommendation. So now they did 3 experimental setups. The first one is with the metrics we just seen. So here, this is symmetric, but the difference between option A and option B for each one of the participants is relatively small. In the next treatment, actually, the receiver gets much larger payoff in option A. So when the sender tells him to choose option B instead, it makes the receiver lose quite a lot, and the sender by itself doesn't gain too much. And the last option is also symmetric, but now the gaps are much higher. So the sender has much more to earn from lying.
Sigal, sorry, I'm confused. So which one is A and which one is B is private information of the sender? Is that the game?
It's not a private information game, but yeah, it's information that only the sender knows.
Only the sender knows. So
yes.
What the receiver knows is that those are the two options, but it doesn't know which one is A and which one is B. And the sender says A or B, or the sender says you should choose the 5-6 option. I mean, something is not clear to me how this exactly works.
The sender can choose exactly between two messages. Okay, one is this message exactly with this wording. Option B will earn you more money than option A.
I see. It says will earn you more money. Okay, I see.
Exactly. This is the exact wording.
Okay, or interchange and or option A will earn you more money. That's all it can say. I see.
Yes.
Okay. But the set of options is known to the receiver. It just doesn't know which one is A and which one is B.
All the receiver knows is that there's one option which is A, one option that is B. That's all.
It doesn't know whether it's in a 5-6 or 5-15 case.
No. It doesn't know anything.
Okay.
Just that there are two options.
Now it clarifies it. Okay, thanks.
Okay, good. Any more questions about this setup? Good. So now what we're interested in is how these different treatments are going to affect the percentage of senders that will lie. So again, lying is recommending on option B here. So in the first experimental setup, only 36% of the senders lied, so recommended option B instead of option A. In the second experimental setup, now that the receiver has much more to lose from option A, then only 17% lied, so much less. And in the last option, which is in last treatment, which is symmetric, now many more of the senders lie. So more than half of them recommended the receiver to choose option B. And this tells us a couple of things. So first, people do lie, but in many cases, people do not lie. So there's significant percentages in here that the sender decided not to lie. And it also suggests that the decision whether to lie or not depends on the sender's benefit from lying relative to the receiver loss from this lie. Okay. So now, based on this research and some of the models that were suggested to explain this behavior, we designed a model for moral bidders. Now, the word moral here is a bit of a mouthful, but what we really mean is bidders that obey the following two behavioral assumptions that are based on the experiments we've previously seen. So first of all, they have a preference for truth telling. And we can see this, for example, from the first experiment, where they don't lie to the full extent. And second of all, when they decide whether to lie or not, they are not only looking on their own utilities, on the effect of lie on their own gain, but they are also looking on what would happen to others. So how much is this going to damage the other players? And based on this, we design mechanisms that are suitable for moral bidders. And at a high level, the rationale behind our mechanisms is that the player is only going to lie if his profit from lying is significant. So if his profit from lying is larger than alpha times the sum of losses of the other players. And here we have the individual preference for truth telling, since the kind of like default state according that our players are comparing against is truth telling. So default is truth telling, and our player is contemplating on whether to lie or not. And when making this decision, he's also thinking about the effect of lying on the other players. So let me be more formal about it. We will consider the following setting. So there is only a single item. To keep things simple, we think about deterministic mechanisms, and we assume our mechanisms are individually rational, so players do not lose from participating, and there are no positive transfers, so we don't allow the mechanisms to pay the bills. And now a mechanism that is alpha moral, okay, and alpha here is a parameter between 0 and 1, is defined as follows. So as usual, the mechanism is a pair, and allocation function f. Here f decides which player to allocate the item to. It can also decide not to allocate the item at all. And p is a payment function based on the player's reports, how much each player will pay. And such a mechanism, we say that is alpha moral if in every instance, v1 through vn, for every player I and value vi, such that player I can increase his profit by reporting v prime I. So it's possible for player I to tell the mechanism a different value than his real value. And by doing so, it will increase the profit. So in every situation like this, we require that the benefit to the player, which is this, would be at most alpha times the damage from this lie to the other players. Okay, so formally what we mean by this notation is this is the profit of player I, that VI is its real value, and now it's reporting V prime I. So if there is a lie that can make him increase his profit, we require that the profit from lying would be at most alpha times the losses of the other players. So the damage he's causing the other players. And if a player is moral, then this means that his profit from lying is not worthwhile the damage he's causing others. So he's not going to do this lie.
So,
okay?
Sigal?
Yes,
So
Sergio.
in other words, it's as if the utility function of the player is his own payoff plus alpha times the payoffs of the others. And now he just acts according to this payoff function. Is that the fact that lying or not lying, you put it here, and it has no effect. I mean, it's just, it's not, it doesn't apply to lying. Or am I missing something?
No, because if we do this, for example, and I'm affecting your payment, then I might, and I care about alpha times your profit, I might say a lower value to increase your payoffs. So no, we don't want situations like this. It's not that like I'm going to even consider lying in order to increase your payoffs.
It's only when I do not say the truth that he looks at this function.
Yeah, this function is exactly kind of, so in a sense, we kind of limit the type of lies that people may consider. What I said.
It's as if his payoff function is the true payoff function when vi prime equals vi, and his payoff function plus alpha sum of the others when vi prime is different than vi.
No, again, because then I can lie. Okay, it's really different. We can't really define it as some of.
I got you. Okay, I got it.
Okay, so it's different from some altruistic utility function. So it's really different than that.
Yeah, that's where I was going, because somehow I saw. I mean, things like this have been done in the past, so I was trying to see if that's where it's going. But you say it's not. Okay.
Yeah, it's different than that. It's really specifically about kind of like the lying behavior. It's not that I'm altruistic. No. Okay.
Sigal,
yeah, Ben.
Why is alpha bounded by 1? Or is there, like, I can't.
In principle, you can think about alpha, which is higher than 1. It just makes sense that alpha greater than 1 would mean that you would like care about others more than you care about yourself in some sense. So like if you're going to benefit X and the other one is going to lose something even smaller than that, then you're not going to do it. Yeah.
Okay.
But yeah, you can think about higher values of alpha as well.
Yeah.
So one.
Yeah. Oh, sorry. How is this different from? So in other games, there are models of altruistic agents, even in games where there's no truthful option, like in congestion games. But again, they have this similar alpha or other parameter to weigh your utility against other players' utilities. Is there something substantially different when there's also the option of truth telling?
It is not exactly the same as altruism, exactly because we only consider this when you lie. It's just that it's really specifically tailored to when you decide whether to tell the truth or to lie, you think about the effect on other people. It's not like a game in which, again, like you completely care about other people and you're going to do things to maximize their utility. Exactly like Sergio said. So in other such games, then you would maximize some utility function that will also have a component that has the utilities of the others. And this is not the case.
So maybe I can just say differently. And so you say here, by lying, you only mean one kind of lying, only lying that improves your own utility. You disallow completely lying which reduces your utility. That's the difference compared to previous work. In previous work, you could lie in the sense that you reduce your own utility and other gains more and you're happy about it. Here you don't allow it. Nobody is going to lie to benefit others if he loses.
It's not that we don't allow it, it's just that we don't assume this kind of behavior. Okay.
Yeah. So in the model, you
Yeah.
don't consider this kind of behavior. This is not a behavior that you are worried about. The only kind of behavior you are worried about is people lying to increase their own utility. You're not.
Yeah, exactly. So the starting point here is that people are still selfish, but are not selfish all the way. Okay, so when they decide how much they care about their own utility, they also think about how much they're damaging others. And kind of lying here is important because there's a big difference also in the literature and behavioral economics between when you actually need to tell the lie. Okay, so in the sender receiver game, it would be between actually telling the other person that you need to make this choice, even though it's the wrong choice, then when you, as say a dictator, need to choose between two different allocations. So there's a big difference between here. So it's really about the action of lying. And since the models about is saying that the action of lying has some cognitive cost, and there are many other related costs to lying. So specifically in this act of lying, then you are going to weigh things differently. It's not that you have a really different preference for utilities or for different allocations. Okay, so it's really about lying.
But I think Oren's observation is still correct, because it seems that you have this discontinuity. If you only care about hurting others if you profit from lying. If you don't profit from lying, you suddenly don't care at all about other people.
But yes, because this is all about lying. Okay, it's not about caring about other people. It's about under which circumstances are you willing to lie. Lying is not something that people do so easily. It has costs. And when you need to incur the cost for lying and you're also hurting others, then you're going to think twice about it and you might not lie. Okay, so this is why you only consider what happens to other people when you contemplate the lie. Okay, so the two are tied together. This is really different than something else that is studied in the literature, which is more related to altruistic and having different preferences to different allocations. So you may favor allocations that are more fair, or you may favor different allocations. This is not that. This is really talking about.
But mathematically, it's equivalent to caring about others if you are lying. In the case that you are lying, it's mathematically equivalent to caring about others.
Strictly mathematically speaking, yes, but not the point in the model. But yes, strictly mathematical speaking, yes.
Sigal, if the sender was like just asked to recommend either A or B without explicitly saying, you know, you will get higher utility if you do a B over A. Do you know if they ran this experiment as well?
So I think they ran versions of this experiment, and when it's just a recommendation, people lie more. Lie more. I mean, people choose the option. It's easier for them to choose the option that is better for them.
Mm-hmm.
Yeah, this and
because they are not lying. No, but that's the point. They are not lying. They say just choose A. I didn't tell you that A is better for you than B. I just say choose A. That's not lying.
Yeah, right. So this support that the explicit lying is actually hurting them, right?
Exactly. Lying. Exactly. It's really about the lying. Yeah. Okay. So one last thing I wanted to say about this slide is that when we take alpha to 0, then this is just a truthful mechanism. Okay, it's a truthful mechanism because what it says that if there is a player that can increase its value, then this increase should be at most 0. So no player can increase its value. So alpha equals 0, zero moral mechanism is just a truthful mechanism. Okay, so let's go over a few examples. We will see 2 of them. To keep things simple, we take alpha equal to 1. And the first thing we are going to see is that sometimes we can implement using one mole mechanism, or alpha mole mechanisms, allocation functions that we can also implement with dominant strategies, with truthful mechanisms, but with different payment functions. So here the allocation is simply allocate to the player with the highest value. In a truthful mechanism, we will just ask for the second price. Here we show that in a one mole mechanism, the payment can, example, be half the second price. And let me show you why this kind of mechanism is one mole. So this is just a reminder of our requirement for one mole mechanism. So again, this is the profit of player I from line. And this is the damage to the other players. Alpha here is 1, so we don't see it. Okay, so we denote by VK, the player with the maximal value, and VJ, the player with the second highest value. And first of all, it is clearly the case that player K cannot increase its profit. This is the usual argument, just as in a truthful mechanism on the second price. The more interesting part is when we look at some other player I that can increase its profit by reporting VK plus epsilon. And since our payment is half the second price, then it's very possible that there is such a player. So for such a player, what we require is that the benefit from lying, which is this, okay, so the value is VI, and if our player decides to lie, he's going to get the item, and the price that he would pay would be VK over 2. So we want the benefit from the lie to be at most the damage to others. And since we have just one item, the damage to others is just the profits of the player that previously received the item. And this is player K, which previously had the profit of VK minus VJ over 2. And it's pretty easy to see that in this mechanism, this inequality holds. So by our choice, VK is greater than VI, and also VK is greater than VJ. So indeed, the benefit of player I from lying is less than the damage to the other players. So player I is not going to lie. Okay?
But this inequality holds for any number instead of 2. No? Or I'm wrong? It's VI plus VJ over 2 less or equal VK plus VK over 2. Instead of 2, you can put any multiplier there. No? I'm wrong? How do you get the 1/2? I mean, why 1/2?
Because I want to make the example concrete. It works for any seed between
it's not anything special. Any number there instead of 1/2 will work just as well.
You are right. It's just to make the example concrete.
Oh, okay.
Okay, so anything like in the between 0 and 1, not 0, but between 0 and 1 would work. Yes, just to have a concrete example. Any questions about this example? Good. So let's see another example. And in this example,
to make it more than 1, you are killing the behavior of the maximum, right? Am I right? You cannot make it more than 1 because because then player K will deviate, right?
Yeah, it's exactly between like 0 and 1. You can't do 0. 1 is second price, but anything in between works. Yeah. Okay, good. So the second example,
so the seller is not happy.
I'm going to get to this. Yes, you're more than one slide ahead of me. No, actually, yeah, one slide ahead of me. Yeah, as usual. Good. So the second example is going to show that we can actually do more interesting things with more mole mechanisms. And we can implement allocation functions that we cannot implement by a truthful mechanism. So we're going to look at the following allocation function. So here the x-axis is the value of v1, of player 1, and the y-axis is the value of player 2. And the different colors correspond to the identity of the player that will be allocated. So in the gray region, we are not going to allocate the item. In the blue region, player 1 will get the item, and in this red line where the value of player 1 is 11/10, player 2 is going to get the item. Now, this allocation function is clearly not monotone. So, for example, if we take v2 equals 1, then when player 1 increases its value to 11/10, suddenly doesn't get the item anymore. And since the function is not monotone, then we know it cannot be implemented in dominant strategies. Now, let's see how we can implement it by one more mechanism. So I need to show you a payment function. And the payment function we're going to choose is the following. If player 1 is allocated, then he's going to pay exactly 1. And on this line, where player 2 is allocated, then he's going to pay 0. Okay, so this is the mechanism. And now we need to show that it's indeed one model. Again, here, this is our condition. So first of all, if player 1 is allocated or the item is not allocated, then player 1 should beat its true value. And the reason here is just the same as in a truthful mechanism. Okay, so in the gray area, if we are here, then player 1 does not have a lie that can make him get the item. So it should be the true value. Here, he can report a higher value, but then his payment would be greater than his value, so he doesn't want to do it. And in the blue area, the payment is fixed, so there is no reason for lying. Now, let's look on player 2. And we distinguish between two cases. So if we are here, the value of player 2 is less than 1/10, then again, this is easy. Clearly, player 2 should report its true value, and player 1 cannot do anything about it. There's no value it can report and get the item. So this is fine. The interesting region is here, when the value of player 2 is at least 1/10. And now player 1 can misreport its value and get the item. And in this case, profit of player 1 for misreporting would be 1/10, since his real value here is 11/10. And when he misreports his value, he gets the item and pays 1. So his profit is 1/10. And this benefit should be smaller than the damage to player 2. So the benefit of player 2 when he gets the item is just v2, the price is 0. And this means that in this case, for the mechanism to be one mole, v2 should be greater or equal to 1/10. And this is exactly the case we are at. So this is where our mechanism differs from a truthful mechanism. Player 1 can lie. It can increase its profit by lying, but the increase is not sufficient to kind of like overpower the damage to player 2. So he's not going to lie in this way. Any questions?
Sigal, if you go back, sorry, I was thinking about the previous example still. If alpha is strictly less than 1, that gives some, it seems to me that will give some real restriction on what you can get. Whereas for alpha equals 1, I think that it's too easy. The fact that anything goes, which means this 1/2 can be replaced by any fraction. But I think, am I right that if alpha is strictly less than 1, that's no longer true, and you get a much smaller set of feasible things? I'm just asking. Have you checked it?
Yes, this example as it is only works for alpha equals 1. You're right.
But you still get new things, right? You always get new things, but it changes with the value of alpha.
So this here, this is more complicated, but this example we can adapt for any value of alpha. So you can get different allocation functions that are not implemented by dominant strategy mechanisms with any values of alpha. And this is what what would be more important.
Yeah, but it's not true in general that this is independent of alpha. That's what I was trying to say. It's not just a small scale. It has some more subtle influence. So I just want to make sure that our intuition from alpha equals 1 is not should be taken with caution.
And another question going in the other direction, going back to Ben's question, what's special? I mean, I see nothing special about the point alpha equals 1. There is, right? I mean, alpha can be larger than 1. And what's special about the point alpha equals 1 that you make it a limit?
Alpha equals 1. So kind of like the only assumption here is that still people are selfish. They care about themselves. And alpha greater than 1 would mean that you care about others more than you care about yourself in some sense.
But well, it's the sum of others.
It's the sum of others, and so we have the luxury.
Assume there are two. Assume there are two.
It's not the fact that we assume there are two. We're just in all of this paper. We are only working on a single item setting, so the sum doesn't really matter. It's only just one player that received the item, and he's going to have a positive profit. So we kind of have the luxury of saying, okay, we will compare against the sum, but you can also think about other comparisons. Like you don't care about the sum of losses, but the maximum loss when you would extend this to more complicated auctions, for example, if compared to all auctions. But here, since this is just a single player, then sum is the same as the maximal loss and etc. Okay. So let's continue. So what we observed from the previous mechanisms is that when we have moral mechanisms, then this extends the set of implemented of allocation functions that we can implement. Yeah, this strictly extends the set of allocation functions that we can implement. And natural question is whether an auctioneer can take advantage of this. So whether an auctioneer can leverage the morality of the bidders in order to increase its revenue, to get more revenue. So now we have more allocation functions, and maybe some of the allocation of these new allocation functions can be useful to get more revenue of the bidders. And the answer here is it depends. It's going to depend on the type of valuations, the type of distributions that the players' valuations are drawn from. So before going to this main question, let me very briefly go over some properties of alpha moral mechanisms.
Sigal, I'm sorry to keep interrupting, but I just wrote it down. When alpha is strictly less than 1, in your first example, you get nothing new. It's only when alpha equals
Sergio,
1. Yes.
It was just an example. Like we can continue discussing it.
But it's a simple enough example that it illustrates something. And you know, it's just a second. I mean, again, I'm not making a theorem out of it. But what I want to say is that alpha equals 1 was crucial. If alpha is strictly less than 1, then nothing else. No, it's not continuous. It's nothing.
Agree.
Yes.
I agree.
Okay.
I agree. It was this specific example. It was just as an example.
It took me a little to work it out. Yeah.
Okay, good. So let's go over some properties. So first of all, one property of alpha moral mechanisms is that they are payment independent. And this means that the price of the winning player does not depend on his value. And this is the same property holds for truthful mechanisms. So I'm not going to go over the proof. It's just the same as the proof for truthful mechanisms. Okay, but it will be useful for our next proofs. Okay, so moral mechanisms are payment independent. The payment doesn't depend on the value of the winning player, the player that received the item. Okay. So here is another proposition, and what this proposition tells us that if we compare between a truthful mechanism and an alpha moral mechanism, both are implementing the same function, then the payment function of the alpha moral mechanism cannot be higher than that of the truthful mechanism. So this is like the first example we've seen, in which so we've seen that in a moral mechanism, one moral mechanism, we can price when we do a second price item, second price auction, we can price at half the second value, but we cannot price higher than that. Okay, and what this tells us when we look for a question for an answer to a general question is that the only possible way to take advantage of moral bidders is when we consider different allocations function. Since for every function it is also implemented by a dominant strategy, then we may have different payment functions, but overall the payment will be just lower. So let's go over the proof. First of all, in both of these mechanisms, the payment for players that are unallocated is 0. Now we pick I to be the player that gets the item when reporting VI, and the others are reporting V minus I. And assume towards contradiction that the alpha moral mechanism can actually get a higher payment from player I to pay a higher payment. Okay, so if this X is the value of player I, then this is the price he would pay in a truthful mechanism, and let's say this is the price he pays in some alpha moral mechanism. Now, since the function f is implemented by a truthful mechanism, it means that it has to be monotone, and this price is the critical value. So in particular, it means that for every value v prime I, which is above the critical value, player I should still get the item. Okay, so when player I value is v prime I, he's still getting the item. Now, as we've just seen, in the alpha moral mechanism is payment independent, which means that both when his value is v prime I and when his value is vi, he's getting the item, and the price should be the same. But here we get a contradiction, since in case of his value is v prime I, we require him to pay p prime vi v minus I, which is greater than v prime I. So this is a contradiction to individual rationality. And what this means is that, again, when we look for increasing the revenue, we need to look for different allocation functions. So allocation functions that are also implemented by truthful mechanisms, we may implement using different payment functions, but these payment functions are not useful in terms of revenue. Any questions? Good. Okay, so the next thing I want to show is an equivalence between alpha moral mechanisms and what we call alpha profit maximizers. And this equivalence is useful since working with alpha profit maximizers is much easier for sake of our proofs. So to define them, we need to define the following thing. So this is a potential payment, and the potential payment is in a payment independent mechanism is just the payment of player I when it wins. So if player I can never win, given the bids of the other players, then this potential payment is defined to be infinity. So if we go back to our example, when the value of player 2 is, say, 2, then the potential payment of player 1, which depends on player 2, will be 1, since if player 1 wins here, his payment would be 1. But if the value of v2 is here, say 1/20, then the potential payment of player 1 is going to be infinity. Okay, and using this potential payment, we can define potential profit. So if the player gets the item, what's going to be its profit? And now with this definition, a profit maximizer is again a mechanism which is individually rational, no positive transfers, and payment independent, such that if there is a player with positive potential profit, then the item is allocated. And if the item is allocated to player J, okay, then for any other player I, the potential profit of player I is at most alpha times the potential profit to player J. Okay, so this is really very, very similar to alpha moral mechanisms, and we will briefly see the equivalence in the next slide. Any questions so far? Okay, so this is a nice illustration of showing that the mechanism we've seen is also alpha profit maximizer, but for sake of time, I'm going to skip it. And let me just show you the equivalence. So essentially, alpha profit maximizer is just a different way of massaging the definitions to get an alpha moral mechanism. It's really the same thing, okay? I'm not going to get into it, but it's practically the same thing. Okay, good. So now we can get to our main result. So the question we ask is, can we extract more revenue from moral bidders? Can an auctioneer take advantage of them? And as we've said, the answer is that it depends. So if we consider bidders that the valuations are done IID from a standard distribution, I will give you the definition of a standard distribution in the next slide, but for something concrete, you can think about uniform distribution. Then the auctioneer cannot take advantage of the bidders. So for any alpha moral mechanism M, there exists a truthful mechanism M prime that extracts at least as much revenue. Now, when we consider correlated distributions, then there actually are cases in which an alpha moral mechanism can extract a strictly higher revenue than any truthful mechanisms. Okay, so these are the two main results, and let me elaborate a bit more.
So Sigal, what about independently but not identically?
So this is the part of the things that we don't know yet. So there are still gaps in our results. I will mention it later.
And Sigal, the correlated, how is it related to like Kramer-McLean kind of results about full revenue extraction?
It's not very related to them.
Not related, okay.
Yeah. Okay, so independent distributions. We're going to make a simplifying assumption that the distributions are discrete and the support is between 0 and 1, and the support is in increments of epsilon. Now, what do we mean by standard distributions? So this, for example, include the uniform distributions, exponential distributions, and formally, these are distributions in which for every Vj greater than or equal to Vi in the support, Fvj, so the PDF, is at least Fvi over 1 plus Fvi. So it's more restricted set of distributions than just regular distributions. Now, one way of, the first way you would have think about going after proving such a theorem is try to extend Myerson characterization of optimal auctions. And this doesn't work. And the reason this doesn't work is the first step in Myerson characterization is characterizing the payment function in terms of the allocation function. And then he can simply forget about the payments and only focus on the allocation function and finding an allocation that maximizes revenue. Now, this approach inherently fails for moral mechanisms, since the allocation function cannot be characterized in terms of the payment function. And we have some examples in which it's almost unconstrained. So we need a different approach to tackle this. And as part of developing our techniques, we are also able to provide an alternative proof to Myerson's characterization of optimal auctions. And this is when the values are drawn from independent regular distributions. So since our proof for the theorem about alpha moral mechanisms is quite involved. Instead, to demonstrate our techniques, I'm going to pretty briefly show you how we can use them to provide an alternative proof to Myerson characterization of optimal auctions. And the proof is going to be for the simpler case in which we have two players that are drawn IID from the same regular distribution F. Okay, but this is not, our proof is more general than this. Okay, good. So for this setting, Myerson tells us that the revenue maximized auction is a second price auction with reserve price, which is equal to the monopolist price. Okay, so this is the price that an auctioneer would ask if there is only one bidder. And exactly the same as a truthful mechanism is zero model mechanism, it's also a zero profit maximizer. And this would be an easier way of thinking about the mechanism. So in the language of profit maximizer, what we need to show is the following. So we need to show that there's a revenue maximizing truthful mechanism such that if the value, if VI is greater than X, it's greater than the monopolist price, then the potential payment, so this is, you can think about it as the price it's presenting to the other player, is its value. So this is what happens in a second price auction. And below the reserve price, below the monopolist price, then the potential payment should be X. So this means that this is the reserve price. Okay. And the main challenge in this proof is showing that when we are above the monopolist price, then the potential payment is at least VI. Once we have this, then it's relatively easy to show both 2 and essentially complete the proof of 1. So we are going to focus on how we show this. Good. So this is what we want to show. We want to show that there exists a revenue maximizing truthful mechanism in which every player, the potential payment you present to the other player is at least his value. And the way we are going to prove it is first assume that there is no such mechanism. And from all of those mechanisms, we are going to pick the one with the maximal value of V1, such that the price V1 presents to the other player, so P1 V1 is less than V1. And from all of those mechanisms, we are going to pick P1 V1. A good way of illustrating this is the following. So the points here play a dual role. So one role is these are the values of player 1, these are the values of player 2, the values in the support. And also, we have these kind of directed arrows, which imply that this is the price that player 1, when his value is V1, presents to player 2. Yeah, and what we want to show is that there exists a mechanism that is still revenue maximizing where we increase the value of P1 V1. We increase it by epsilon. So we are going to get by doing this, we either get a contradiction to the fact that the original mechanism maximized the revenue, or we are going to get a contradiction to the maximality of the way we chose the original mechanism. First, we noticed that because V1 is the maximal such that P1 V1 is less than V1, then all of these values, the payment is going to be greater than the value. So for each V prime 1 here, the payment is greater than V prime 1. In particular, and a weaker climate will be sufficient, is that all of these values present payments in this region above V2. And the other direction also holds, and this holds because of feasibility. So assume there's a value of player 2 here that presents a price less than V1. Then in this case, we have a contradiction to feasibility. Since in the instance V1, V prime 2, both of the players are profitable. And this is something that cannot happen in a truthful mechanism. Now, this point by itself is very easy to show in truthful mechanism, since in truthful mechanism, we cannot have two players with positive profit, but this is exactly the reason why the proof for alpha moral mechanisms is first more challenging, and second, why it's weaker in the terms of the distributions that are handled than the proof for truthful mechanisms. Okay, so this is what we know. And okay, let me go over this quickly. So we want to see now what happens when we increase the payment that player 1 presents to player 2. So now I'm going to go over this very quickly, but just to give you an idea. So this is how the revenue changes. And the interesting case here is when V2 presents to V1 a price that is greater than V1. And in this case, because of this case, we cannot simply say that when we set P1, V1, when we increase it by epsilon, the revenue increases. So we need to handle this case more specifically. And we, at the end, reach a state where we are making two changes in the mechanism. So one, we increase P1, V1 by epsilon, and two, we decrease P2, V2 by epsilon. So we're making two changes in the mechanism simultaneously. And what we get now is that when we look at the effects of both of these changes simultaneously, then this is these two changes are going to, on one side, increase the revenue, and on other cases, decrease the revenue. So we wanted the increments to be greater than or equal to the decrements. And we ask, when would this happen? So if we rearrange it, we get this. This is very similar to virtual valuations, since this is actually the discrete part of definitions for virtual valuations for discrete distributions. So this means that the virtual valuation of player V1 is at least the virtual valuation of V2, and this holds for regular distributions. So the bottom line here is that if the valuation, the distribution is regular, then we get a contradiction either to the fact that the mechanism we started with was revenue maximizing, or to the fact that it was maximal. Okay, so now very briefly, quality distributions. So we showed that there exists a distribution in which an alpha moral mechanism can extract a higher revenue. This is a very not detailed sketch of the proof, which I'm going to skip. And an extra interesting result is that even though the revenue of an alpha mechanism can be higher than that of an optimal truthful one, it can be at most twice the revenue of an optimal truthful mechanism. And the idea here is showing that Ronen's look-ahead auction provides a true approximation not only to the best truthful mechanism, but to the best alpha moral mechanism. So let me just summarize. Our work joins the growing literature in algorithmic game theory, incorporating behavioral assumptions into well-studied settings. We develop and analyze mechanism for moral bidders, so bidders that obey two behavioral assumptions regarding when they're going to lie. We've seen a difference between whether the auctioneer can increase the revenue based on whether the distributions are standard and bias or drawn IID, or for correlated distributions. And our proof techniques also enable us to present an alternative proof to Myerson characterization. There are a bunch of open questions. So first of all, close the gaps. So can we say, can we increase our results on the inexistence of moral mechanisms that extract more revenue for regular distributions, or what happens when the distributions are not regular? And if we think about truthful mechanisms. So can we use our techniques to get a characterization of truthful mechanisms beyond regular distributions? And on a higher level, it will be really interesting to see how we can apply more mechanisms to other settings. So for example, combinatorial auctions, and considering other relaxations to truthfulness. So that's all. Sorry for taking more of your time than expected. And, yeah, any questions?